Welcome to the Math 1, Unit 8, Lesson 5, summary video, Giant Parthenon Wheel. This lesson is a develop understanding task, which is meant to introduce you to a concept, but not necessarily finalize rules or strategies. The purpose of this lesson is to surface ideas about projectile motion and access prior knowledge of distance and rate problems to build quadratic functions in standard form by identifying and interpreting the constant, linear, and quadratic terms. Ignoring air resistance, the following graph shows how far an object, a bowling ball, basketball, anvil, etc., will fall after 0, 1, 2, and 3 seconds. So in this lesson, we're dealing with projectile motion. So when we look at the graph that's been given to us, we can see that we are starting at 0 seconds and the distance traveled is 0 feet. And at 1 second, it's 16 feet, and 2 seconds, it's 64 feet. And so we can see that this is increasing. We know that our x-axis represents our time that has passed since the object has been dropped, and the y-axis represents the distance from the point where we drop the object. So it's increasing, and it's measuring how far away from the point of release the object is. And so we're asked to create multiple representations for this and to also look and see what patterns we can find. And so the first thing I notice is when I look at 1 second and 2 seconds, there's a couple different patterns that I notice. I notice that if I take the second and I multiply it by 4 and square that number, I get these numbers. So I know that the square root of 144 is 12, and if I divide 12 by 4, I get 3. The square root of 64 is 8, and if I divide that by 4, I get 2. The square root of 16 is 4. If I divide that by 4, I get 1. So I'm noticing that I can take the input, or the time, multiply it by 4, and then square that number, and I get these outputs, or the distances. Another way I can think about it is these are all multiples of 16, and so if I divide this by 16, I get 9, which is the square root of 9 is 3. So if I square the time and then multiply it by 16, I also get these outputs. So if I square 2, I get 4, and 4 times 16 is 64. If I square 1, I get 1, multiply that by 16, I get 16. And so I have represented this in this table. So t is my input. These are my values on my x-axis, my independent variables, and my dependent variables are my outputs on my y-axis. This is the height, or the distance from the point at which the object was released. And so we can see that these are increasing. This second column represents the value that I get if I square the number first, square my time first, and then if I multiply these values by 16, I get these values. The third column represents multiplying 4 by my time. So if I multiply 1 by 4, 2 by 4, 3 by 4, and then if I take these values and square them, I get these. So I can think about it either way. And so when I'm looking to write the equation form of this function, I'm trying to look for patterns. And so I'm looking to see, is this a linear function? Is it an exponential function? Because these are functions that I'm familiar with writing the equations for. And so I'm looking for a common difference or a common ratio. And so I notice that there's no common ratio. And when I look at the difference, there's no common difference. So that tells me that it's not linear and it's not exponential. So then when I look at these differences, the difference of these differences I see a pattern there. And this is referred to as the second difference. So these are the first differences of my outputs, and these are the second differences. And a common second difference is a characteristic of quadratic functions. So this is the first expression that we talked about. This is taking our input, multiplying it by 4, we get these values, and then taking these values and squaring them. And so this is one way that I could write this function. And this represents the second way that we can write the function. This is taking my time and squaring it first, giving me this column, and then multiplying these values by 16. Now notice that these are in fact equivalent expressions or equations, and I know this because regardless of which one I do or I use, I'm still going to get these same outputs. So I'm using the same inputs, I'm getting the same outputs, I'm just going about it two different ways. Additionally, I know that if I were to distribute this 2 to the 4 and to the t, 4 squared would be 16, t squared would be t squared, so I would still end up with 16 times t squared. Keep in mind that this is the simplified form, and so this is the form that we would want to use. Here's the next problem. While sitting at the very top of the giant Parthenon wheel, Sam accidentally drops his sunglasses. His sunglasses will fall given the same rate as the graph on the previous page. The top of the giant Parthenon wheel is 256 feet above ground. So we know that it's going to fall at the same rate. And so on the left side, I have the table and the graph from the previous example, so that we can reference that. And so when we are creating we're asked to create multiple representations to model the height of the sunglasses from the ground over time as they fall. And so what's the first thing that's different about this is in the previous example, we were modeling the height from the point at which the object was dropped. Now we're modeling the height from the ground. So in the previous case, we saw the height increasing because it's getting further away from the point that the object was dropped. In this case, we see the height decreasing because we're measuring from the ground, the height from the ground. And so when it starts at 256 feet, it's going to decrease until it gets to a height of 0. So we notice again that these are increasing, so our differences are increasing. Both our first and our second differences are increasing. Here, because our overall height is decreasing, the differences are decreasing. So to go from 256 to 240, we are subtracting values to get to the next output. Additionally, to go from negative 16 to negative 48, we're subtracting 32 and subtracting 32. What we notice though is that the values, the absolute values, are the same because they wanted us to use the same rate. And so if the first difference here was had an absolute value of 16, we need the first value here to have an absolute value of 16. Same thing for the second, 48 and 80 and so on. And again, what we notice is that we end up with a common second difference here of negative 32. And so this is what the graph would look like for these ordered pairs. So again, our x-axis represents the fall time in seconds, and this is the fall distance from the ground. We're measuring from the ground in feet, and so we're starting at 256, and at 1 second we're down to 240 feet, at 2 seconds 192 feet, at 3 seconds 112 feet, and at 4 seconds we're at 0 feet, or we're on the ground. When we look at the equation used to represent this scenario, just like in linear functions, our constant term represents our starting point. And so we're starting at 256 feet above the ground, and so that's a positive value. And we're changing at the same rate that we changed in our previous problem. And so this term right here isn't going to change because we already discovered what this term was in the previous problem. And so we're going to talk about that more in a little bit. In the previous video, we talked about this being in standard form. And so if we look at this in factored form, we know that if we take out the greatest common factor, which is a negative 16, and I'm taking out the negative as well as the 16 because I want to leave this squared term as a positive term. And so we're always, whenever we can factor out, we want to leave the term, the variable that's raised to the second power, we want to leave that positive. So we're factoring out a negative 16 from this term, and we're left with t squared, and we're factoring out a negative 16 here, which leaves us with negative 16. And so then if we take it a step further, and we write the binomial factors that make up t squared minus 16, we have t plus 4 and t minus 4. And again, just reviewing what we've done in the previous videos, if we distribute the t to each term in the second factor, we get t squared minus 4t. And if we distribute the 4 to each term in the second factor, we get 4t minus 16. So we have t squared minus 4t plus 4t minus 16. The plus 4t and the minus 4t represent 0, so we're left back with this t squared minus 16. And then in the previous video, we talked about setting each of these factors equal to 0 using the zero product property. And what that tells us are the values that t could equal that would make this function true. And in this scenario, we know that t represents our time in seconds, and our time can't be negative, so this can't be a solution to this original function. And so t equals 4, where we see that on our graph, is here, and what that tells us is that it's going to take 4 seconds for the glasses, if they're starting at a height of 256 feet above the ground, and we're going to talk about this term in a minute, but if this is being applied to the glasses, it's going to take 4 seconds for them to fall and hit the ground. So now we are going to talk a little bit more about this term. So this term is the acceleration due to gravity. And what it represents is 16 feet per second. That's the rate at which these glasses are falling due to the gravitational pull. And so whenever we are dealing with projectile motion problems, this is the term that we are going to be using for our quadratic functions. So all projectile motion problems will need to have this term. Now again, keep in mind this is feet per second. Sometimes with projectile motion problems you may see another term representing meters per second or kilometers. So this represents feet. And the other term represents our initial height, just like it does with linear functions. In our third example, it says, suppose Sam didn't drop his sunglasses. In fact, he was having an argument with his girlfriend who took his sunglasses and threw them downward with a velocity of 96 feet per second. What effect would this initial velocity, v sub 0, have on the equation, table, and graph? And how long would it take his sunglasses to hit the ground? So velocity is the rate of travel of an object. It's similar to speed, except speed doesn't account for direction, whereas velocity does. So again, it's the rate that the rate of travel for an object. And so they give us this equation and they tell us that the velocity is 96 feet per second. So this is the initial starting point, the starting height. This is the acceleration due to gravity, and this is the velocity. This is the speed, or this is the fact that the girlfriend threw them instead of them just falling. And so they don't just have the acceleration due to gravity, they also have some force behind it. And so you can see how we took the same equation, but we now substituted in the 96 feet per second for v sub o. And when we factor out the greatest common factor of -16, we're left with this trinomial. And when we put this in factored form, remember this is standard form, when we get it down into this factored form, we have -16 times t plus 8 times t minus 2. And then when we use our zero product property to solve for, we set each of these factors equal to 0 and solve for them, and we end up with t equals -8 and t equals 2. Again, the t represents time in seconds, and so to have negative time doesn't make sense, so this would not be a valid solution for this function. The t equals 2 would. And so what that tells us is that at 2 seconds, it would take 2 seconds for the glasses to hit the ground. We're using the as far as looking at the table, we are looking at the first difference and the second difference again. We know that at 0 seconds, it was 256 feet above the ground. That's our initial height. And we know that at 2 seconds, it was at 0. And we can substitute in our 1 and our 2 for our t's here and simplify in order to find our outputs. When we look at our first differences, we see that this has a difference of -112. So we're subtracting 112 to get from 256 to 144, and then we're subtracting 144 to get to 0. And they have a common second difference of -32. These negatives represent that direction. So I mentioned the difference between speed and velocity, and how speed is the rate at which something travels, whereas velocity is also direction. And so we see that the distance is decreasing here, and so we can also see our velocity, our direction, we're decreasing here, and we can see how the distance from the original starting point is also decreasing. And this is what it looks like on a graph. So we've got our fall distance, the distance from the initial height of 256 feet at 0 seconds. Here's 1 second, and here's 2 seconds, which is how long it takes for the sunglasses to hit the ground. And so this graphic deals with projectile motion problems. And we can see that if this is the initial height, this is the velocity, the effective velocity on an object. And so we can see that this is linear. However, even if we throw an object up into the air, at some point it's going to curve and start coming back down towards the ground. And so that is the effect of gravity. So when we throw it up, that's the effective velocity. When it hits its peak and then it starts coming back down, it's because gravity has taken hold of it. And so when we are looking at velocity, the height is determined by the rate times the time plus the initial height. So that rate times the time, that is the velocity, and then we add in that initial height. The effect of gravity, we're still taking the rate times the time and adding in the initial height, but now we're also adding in the acceleration due to gravity, which is the -16 t squared. And so if we look at a linear function, which we've been dealing with for several years now, We know that the first term in our linear function is the rate of change, and the second term is the initial height. When we look at quadratic functions, we still have those terms. Our linear term now still represents our rate of change, but now we call it velocity when we're dealing with these projectile objects. And then we still have the initial height as our third term, which is our constant. And so this linear term will have a variable attached to it to the power of 1. But now with quadratic functions, we have this third term. And this third term is our quadratic term, and it's the effect of gravity on a projectile, which is our acceleration due to gravity.